Not there. Okay, good afternoon. Today we will be talking about linear programming, and what we have seen so far is unconstrained linear programming, where we just have an objective function and we try to maximize or minimize it. We saw the univariate, multivariate techniques that were used. And today, actually, what we want to do is what we have now is that we want to add constraints to our linear objective function. So we have a linear objective function, and now we want to include a couple of constraints which are also linear in nature, and we want to solve such a kind of problem. So this kind of problem, the linear programming, was actually the first kind of optimization problem that was introduced. I think it was in 1940s, and it was used in the military actually at that time. So what other sophisticated techniques have appeared since then, actually built on linear programming. So linear programming was the very first optimization problem and the technique. And then other types of problems just sprung out of this, okay? So today we'll be talking about, yes, linear programming with constraints. So let's begin. So as you know that optimization is either maximizing or, okay, let me just okay, it's about minimizing or maximizing an objective function. And what we want to do is now we want to have limit the resources that we have, okay? And so there are some constraints that will actually confine or even further reduce our feasibility set of solutions, and we have to now see how we can solve such problems. Today we'll be learning about a technique called simplex method for linear programming problems, okay? So to begin with, let's start with a toy example, and the toy example is this one given over here. Suppose you want to become a candidate for some political party, you want to become the mayor of a city or something, and you want to win the election in your city, okay? So you divide your city into like some what we say areas, and suppose that we have three areas. One is the urban area, one is the suburban area, and one is the rural area, okay? So you have a city, you have three areas, and the number of eligible voters in each of these areas is given as 100,000, 200,000, and rural is 50,000 voters, okay? And we know that in all elections, not all people, all eligible voters actually go to the voting polls. Some of them vote, some do not. So we know this, okay? So what you want to do is that you have some amount of money that you have to spend in order to advertise for your campaign and to attract voters, right? So what you want to do is you want to know how much money or what is the minimum amount of money you need to advertise on a number of topics in your agenda, so that at least half of each of these areas or sections vote for you. Okay, so at least 50,000 from the urban part vote for you, 100,000 from suburban vote for you, and at least 25,000 from the rural vote for you. You want to get at least half the vote, and that actually guarantees you as the winner. Okay, so that's the problem statement. And now let's see what we plan to do is we want to formulate this in a linear form. So what we have over here is, now your agenda, what are the topics on your agenda? Suppose you want to, I don't know, improve the infrastructure, road infrastructure of your city. So you want to build more roads. Like for example, gun control. Do we have guns in this country? Can you buy guns legally?
Yes, we have, yes.
Really?
Yes, but you have to get to different checkings and only then 5 years, one sort of gun, and then you can get like
Wow.
automatic rifle.
Okay. Didn't know that. I thought no. Okay, good. Uh, well, this is so these are the two topics, and the third one is farm subsidies, like trying to reduce the cost on certain like electricity, water for the farmers, and gasoline tax. I'm sure you guys have this over here. So these are the four topics that you have in the agenda, and you want to advertise or campaign on this. You want to say, okay, if I become the mayor, I'm going to do this, I'm going to control this, I'm going to improve, add subsidies, and I'm going to reduce the tax. Okay. And you have these three areas as we talked about. And what you have to do is on each of this issue, in order to advertise, you need to spend $1,000 on each of these issues. Okay, so every time, so for example, if you look at this table and these numbers over here, it means that okay, so this is in thousands. Okay, so when I say -2 means if I invest, or if I invest on this topic in my campaign, okay, if I, like, for example, I talk about building roads in urban area, I would lose 2,000 voters. Okay, minus means losing. But if I talk about this topic in the suburban area, they like it, so I would actually win 5,000 voters. Okay, so now what you want to know that how much money you have to invest for each of these topics, okay? And what would be that minimum amount that you need in order to get at least half of the vote from each of these sections, okay? So you're given this table, and now you want to see how to minimize your total campaign cost, all right? So this is a problem statement. I just said it. I just read it out to you. So you want to find, you need to minimize the amount that you need to spend in order to win 50,000 urban voters, 100,000 suburban voters, and 25,000 rural voters. Okay. So one approach to do this is, well, you can do the exhaustive trial and error. So every time you add, you try with all the possible combinations, and you see which one actually which minimum cost would actually satisfy this constraint for you. Okay, so but you have to try all the possible combinations. Okay, well, this is going to take very long. So probably there should be a better strategy to solve this more efficiently. Okay, so for example, you could say, what happens if I put $20,000 for advertising on building roads, no money on gun control, 4,000 for farm subsidies, and 9,000 for gasoline tax. So if you have this amount, so this is the budget you intend to invest for each topic in your agenda. If you go back, how do we go back? Okay, if you go back over here, so you keep this table in mind. So basically what you're doing is, so I'm going to spend 20,000 times -2. Okay, so if I spend 20,000 on this, building roads in the urban section, I would get this, and no gun control, so 0 times 8, 4 times 6, that means 4 times 0, sorry, 4 times 0. Okay, so I won't get any vote if I talk about farm subsidies in urban areas, because people in the city, they don't care much. And 9 times 10, which would be $9,000 into 10,000 voters. Okay, so this would be the number of votes that I would get from the urban section. Okay, so if I multiply that over here, I'm sorry, this would be 10,000 votes. So that's what I need, half of the urban. And then I do the same thing for the second column. That would give me 100,000, which is good. And I do the same thing for the last column, would be 82,000, which is more than what I expected. Okay, and that is more than what I wanted. So in total, if you add up this 20 plus 4 plus 9, it gives me $33,000. So with $33,000, using the trial and error approach, I see that I can actually win the maximum number of votes from each section. But we want to do it in a more efficient manner. Okay, so probably, or basically, we can actually even further reduce this to satisfy this constraint that we want. Okay, so we can achieve our goal by spending even much lesser. How do we do that? Let's define 4 decision variables, or 4 variables as such as given over here. Oops, sorry. What happened? So let's define X1 to be the number of thousands of dollars you want to spend on the first item in your agenda. That means on this guy. Okay. Then let X2 be the amount of money you want to spend in this in terms of thousands of dollars. X3 for the third item, and X4 for the fourth item. Okay, so these are the unknowns, right? We want to know how much money we want to spend on each of these items, and the order of the money is in thousands of dollars. Okay, so we define these 4 decision variables. So far, simple. Okay, and then now what we do is, what we can write is that, okay, so now we have these constraints. To win the urban in the urban area, I need at least 50,000 votes, right? So I should say, I should take the first column of the table. Okay, so I say minus 2 times x1 plus 8 times x2 plus 0 times x3 plus 10 times x4 should be greater than equal to 50,000, because I need at least 50,000. Okay, so even if it's greater, it's okay. Okay, so this is what I get for the urban area. I do the same for the suburban and the rural area. I get this. So now I have my constraints ready in terms of my decision variables. Is it clear, guys?
Yes. So
okay, good. So this is it. And now what is the objective? What is the aim? What is the purpose of doing this? The purpose is that the sum of all these decision variables, the amount of money I spend on each of those agenda items, should be minimized. So therefore, I should minimize the sum of x1, x2, x3, and x4, given these three conditions. Okay, so these three are my constraints, and this is my objective function. You see that the objective function as well as the constraints are linear in nature. Okay, so it's a linear summation. Okay, and therefore, if you want to put it in an optimization format, this is how it would look. So you would have minimize the objective function, which is the sum of all the decision variables, subject to these three constraints. And obviously, this fourth constraint is something that always tags along and is always there. Okay, and we always assume that our decision variables are non-negative. And that's well, you may think that why do you have this non-negative? What happens if they are negative? Well, decision variables, normally when you use linear program problem, you're either trying to minimize or maximize some value which cannot take negative amounts, okay? Like you want to find the minimum number of vaccines you need to distribute in a given population. So minimum number can never be -5. It's either 0 or some positive value. With that logic in mind, that's why all decision variables in linear programming are taken to be non-negative. So this is something that you always put in every LP problem, okay? But the three main constraints were how to drive the three main constants was just told to you using that table, and you have to therefore define 4 decision variables for this particular example, okay? So this solution, this problem has a solution, and finding the solution, to find the solution, we will be learning about what is known as the simplex method, okay, today. Let's make our, this was an example. Now let's try to mathematically approach the simplex method. So before that, we need to formally define the LP problem. So it is a linear function. Okay, so you have this a1 x1 up till an xn summation, where a1 and an are the coefficients, and you have n number of decision variables, which are denoted by xi's over here. Okay, and in your constraints, so basically your constraints can be of 3 types. You can have an equality constraint where you have some linear function on the left-hand side, and you have an equal sign, and on the right-hand side, you have a positive value, okay, some positive b, okay? So this is known as a linear equality. And you can have 2 types of linear inequalities, where you have a linear function less than equal to some positive b, or and a linear function greater than equal to positive b. So in some in any linear programming problem, you can have constraints of all 3 types. Okay. So this is known as linear equality, and this is known as linear inequality. Okay, so these are the types of constraints that you can have. The only condition is that in a linear programming, the objective function and constraints should be linear in nature, should be a linear function. That means a summation of products of the decision variables. Okay, guys. Next. For example, now let's consider a linear problem. This is another example. For simplicity, let's say that we have 2 decision variables, x1, x2, and we have basically 3 main constraints on them, where you see that there are 2 inequalities which are less than equal to, and 1 inequality which is greater than equal to, and obviously this one which is always a default. Okay. So now, basically, if you have a bunch of constraints, what happens is now your area in a linear program, remember that the feasible area or the feasible region will always be a convex set. Okay, that means any 2 points in that region, Therefore, if I want to draw it for you, so whatever, so if you are bounded by these constraints in a linear programming, it will always be some what we call a convex hull or a convex, where, well, this is not, let's assume that this is a bad drawing, sorry. Okay. So let's take a polygon. Okay. So what happens is in a convex hull or in a linear programming, the condition is that the constraints always and the objective function, they always actually create a feasible set of solutions, which is in the form of a convex hull. That means all the solutions lie in a convex set. And what do you mean by convex set? That means if I take any 2 points within the set and I draw a line connecting them directly, points on that line will also be solutions within the set. Okay, so for example, this guy is not a convex set, because if I connect this point to this point with a direct line, you see that this part have points which is not in the convex set. So this is not a convex hull or a convex. So in linear programming, it's always guaranteed that when you have a when you have constraints, okay, and bounded constraints, you would always have a convex, and therefore there will always be, so any local or minimum or maximum will always be equal to the global minimum maximum. So there'll be always one global maximum solution for you, okay, or minimum solution for you. Okay, is it clear? Yes. Okay, I'm assuming yes. So let's assume now what we want to do is, given this problem, we want to actually plot the graph. This is again something very simple, which was in your exam, and I just want to give you a visual understanding of how linear programming works. So what I'm doing is now I'm going to plot these 3 lines, okay, and actually these 4 lines, and I'm going to show you the convex hull or the convex set within which the feasible region or the feasible solutions lie, okay? Mouse. So this is it. So this is the set. So these are the 3 constraints. This is 1 line, 2nd line, 3rd line. And since x1 and x2 were taken to be non-negative, that means we look at the first quadrant of the xy coordinate axis, okay? And therefore in that, so everything, so that means x1 should be greater than 0. So it's everything in this area. X2 should be greater than 0, greater equal to 0. So everything up here. And then you have these 3 constraints. So the shaded area is basically the area in which your solution lies. Then what you do is, this is very simple, okay? So now you have this shaded area, which is your feasible region, and you see that it is a convex, right? Any 2 points you connect over here within this area, and you connect them by using a direct line, will have all the points on the line within the same region. So this is a convex hull. And then what you do is, you just plot this line, x1 plus x2. So for example, x1 plus x2 is equal to 0 will be this point. And if you have a 2, 4, 8, you have this line. So what you do is basically you take this line, it's like a ruler or a ruler, okay? You take this line or with whatever, so for at point 0, you draw the line and then just shift the ruler in parallel. So every other value, if you replace 0 with 4, 2, 8, 7, it will be parallel to this line, right? So what you do is just shift this line, and the last point that this ruler leaves this set is actually your maximum point. Okay, and that's very obvious. So for example, in this case, if I take this and I just parallelly move it along this region, so the last point at which this line leaves this shaded area would be your maximum value. And so in this case, it is x1 equal to 2 and x2 is equal to 6. And you plug in x1 and x2, which will be equal to 8. So this function or this objective function has the solution, a global solution, which is equal to 8. For x1 equal to 2 and x2 is equal to 6. Graphically, it's very easy to solve. Any questions so far?
No questions.
Okay. So what I've done is I have obviously I had written down the notes and I have uploaded lecture 6A, which is actually my handwritten notes on this topic, and I was following your main reference book, and So you can go through that, but in your book, like it talks about standard form and doesn't talk about Slack form. But then I think after that, I decided to make a slide so that I think it would be more easier for you guys to explain, to understand. So in this approach, I'll be talking about the two lectures that I've uploaded. Now we are looking at lecture 6B. Okay. So over here, what I have is that first of all, we have two forms, standard form and Slack form. So if you're given an LP problem, okay, with constraints which are with inequality constraints, okay, what we have to do first is if we want to solve it using the simplex method, the first thing that we have to do is we have to convert it into a standard form. So in the exam or quiz, if I give you a LP problem and I say write this or convert it into the standard form of an LP problem, this is what you have to do. Standard form basically means that the objective function should be always maximized. Okay, if it's minimized, we have to convert it into maximize. And your constraints should always be in the form of less than equal to, except for the last guy. This guy is, you know, he's a free guy. He can do whatever he wants. Whatever means he's always there, and his constraint is always greater than equal to 0. It cannot be less than 0. But the only thing is that in a standard form, this should be maximized, and the constraints should all be in the form of less than equal to. So if it's if there is an equality constraint, you have to convert it into less than equal to. If there is a greater than equal to constraint, you have to convert it into less than equal to. Okay, so basically you can have m inequality constraints of this form. And obviously, since you have n number of decision variables, you will have n number of non-negative constraint for your decision variables. Okay, so in total, you'll have m plus n number of constraints if you assume or you consider this as a constraint, which actually is. Okay. So understood standard form. If I ask you to write anything in a standard form, your objective function should always be maximized, and your constraints, except for the last one, should always be in the form of less than equal to. And I'm going to show you today how we do that. Okay. Okay. And if you want to write it in the matrix form, so basically this would be in the matrix form. So C transpose times X, where X is a vector of the scalar decision variables, and A times X less than equal to B, where A is a matrix and B is also a column matrix, and X is always greater than equal to 0. This is a 0 matrix. So obviously, if you find solutions, there will be multiple solutions for X. Okay, because they all probably will many of the solutions will satisfy the constraint, this constraint, and therefore those solutions will be known as feasible solutions. Okay, so if I ask you to find one feasible solution for a LP problem, it doesn't mean that I want you to find a global or optimal or a global optimal solution. Okay, any solution. If I go back to the graph that we drew earlier, excuse me. So your solution could be this point. Oops, sorry. Your solution could be this point, this point, this point, or this point. Any point in this area is a feasible solution. But if I ask you to find the optimal solution, that's only one, and that is this point. Keep that in mind, okay? Okay, so that's about it. So if and also if there is a solution, or if any X value that you get doesn't satisfy any of these constraints, obviously it's an infeasible solution. It doesn't fit into it. It cannot be considered as a solution to this problem. And sometimes the solution can be unbounded. What do you mean by unbounded? If we go back over here and assume that this line, this constraint, okay, 2x1 plus x2 less than equal to 10 does not exist. Okay, and let's say that these two lines are actually not in this direction. Let me draw a graph for you. Assume you have a graph like this. You have one constraint here, and you have another constraint going like this. Okay, if I do not have a constraint which over here, so let's make it in blue purple. So if this purple line is removed, you see that every point, how do I shade now? I would like to shade this area. Every point within this area, if this purple line is not there, every point within this area and this area actually keeps going. There is no bound. Would be a feasible solution, and it would have infinite number of solutions because we do not have that purple line. And therefore, you would say that it is unbounded, okay? So you will have many, many solutions for that. Is it clear?
Yes.
Good. And unbounded, I told you the meaning of unbounded. And now, okay, let's see how to convert any linear problem into its standard form, okay? So let's see, what are the problems that may occur and how do we handle them? So there are many cases where a linear programming problem given to you may not be in a standard form, and these are the 4 possible cases. Oh, yellow is nice. The first one is when the objective function is a minimization problem rather than maximization. So as I told you, it should always be maximization. The second case is when the last constraint, the default constraint, is a non-negative constraint. That means there is no constraint on the decision variable. So we have to make sure that that exists, okay? There might be an equality constraint, and so we have to make it a less than equal to form. And there might be an inequality constraint of this form, which we have to convert to this form, right? Now let's see one by one how we do that. Okay, so this is the first and most simplest form is this guy. You have a problem, let's say this is a given LP problem that I have, and I ask you to convert it to standard form. The first thing you look at is it's minimize, not maximize. So I told you if you want to maximize or change from minimum to maximum, maximum to minimum, what you do is just multiply the objective function by a minus sign. So if we have this objective function, I make this maximize, and I multiply this whole thing by -1. So -1 times -2x1 will be 2x1 minus 3x2. As simple as that. Everyone understand? So over here, only I'm showing you how to correct the objective function and write it in the standard form. Now we look at this, the constraints further. Okay, so this is simple. Now, what do we want to do? We want, okay, so now look at this example. We have this guy, so we have maximized him, good job. Now we have 2 constraints, forget about them, look at the last one, the default constraint. We have 2 decision variables, x1 and x2, but we have only specified that x1 is greater than equal to 0. We have not limited or bounded our x2 decision variable, which is wrong. As I told you in linear programming, x1 and x2 decision variables always non-negative. So we have to kind of include that. How do we do that? It's very simple, okay? So we have x2. So what I can say is that I can define x2 as x2 prime minus x2 double prime. So I can find two variables, x2. I can define 2 variables, x2 prime and x2 double prime, such that x2 prime is greater than equal to 0. And x2 double prime is also greater than equal to 0. Okay, so I add these 2 new guys over here and I write this constraint. Now I choose these 2 in such a way that their difference will be some x2. Okay, is it clear? So for me, it doesn't matter now whether x2 is positive or negative. What is important is these 2 new guys should be greater than equal to 0. So wherever I see x2, I plug in this. I replace x2 with x2 prime minus x2 double prime, and I would get this. Is it clear, guys?
Yeah.
Yes, Professor.
Okay, good. So now what I did is now I solved this last, I also corrected the last default constraint. I corrected this maximize. Now what remains is this naughty guy, and we'll see how to do that. Next, we want to change this guy. Oh, sorry. We want to make this into the form of less than equal to. This is very simple again. We know that if x is equal to y, then this implies that x is greater than equal to y and x is less than equal to y. Is it true?
Yes.
Yes?
Yes.
Okay, so it's less than because equal to, this was covered. So what I do is I just replace this equation with these two equations. So instead of one equation, now I add two equations. So this less than equal to 7, check. Second one should be greater than equal to 7. But now again, since it's greater than equal to, I have to make it in the form of less than equal to, so multiply both sides by -1. So when you multiply -1, you will get minus x1 minus x2 plus x2 less than equal to -7. Now you see that all these actual constraints are less than equal to, the last default constraint is checked, and this optimization is checked. Now I can say that this guy is in the standard form. Okay? Any questions? You won't have any other case or any other scenario other than all these 4 cases that I've talked about. Okay, so it's very easy. Okay, good. Now we want to convert it into Slack form. The reason why I have chosen to explain it in 2 steps, that means first convert into standard form, then into Slack form, is so that I can explain to you what's the meaning of a Slack variable, and that will be needed in explaining the simplex method. Okay. Now, the Slack form is now, so whenever I ask you, I give you some LP problem and I say, write it in the Slack form. First, you have to convert it into the standard form. Okay. Once you have the standard form, it's very easy to convert it into the Slack form, and I'm going to show you how. Okay. So basically what this guy is saying, in the Slack form, all the constraints of this type, except for the last one, should be converted into equal. Okay. So once you have everything less than equal to, now make them equal. That's what I want to do. And how do you make them equal? Make them equal by adding a Slack variable. So basically, if you look at this, so all the constraints are of this form, right? So they are less than equal to in the standard form. We have all the constraints except the last one in this form. Now we want to convert this into a form where we have equality sign. So we know that the BI, the right-hand side, is greater than or equal to the left-hand side. Okay, that's what we saw in the standard form. So what we say is now we move this guy on the left-hand side to the right-hand side. So we get this, and their difference, we define it to be some Slack variable S. So what I did is I included a new variable S, which is some non-negative value, obviously, because this is greater than equal to the left-hand side. And I include that in our last default constraint. So I include S as a new Slack variable, and I define the constraint, redefine this constraint as a form of equality variable. Is it clear? Anyone, any questions so far?
Not yet.
Not yet, good. Now, so given the example that we saw earlier, this is what I did. I've written it in this form. So let's look at the example over here, okay? So what I want, so maximize this is as such, we do not touch this guy. Oops, okay. Now over here, this is less than equal to, right? So what I do is I move this entire thing on the left-hand side to the right. So it becomes 7 minus this thing, and I equate it to some x4. So I define x4 equal to 7 minus this whole part, right? Then this part, again, I do the same thing. x4, x5 is equal to minus 7 minus this whole part. And then again, finally, we have x4, 5, 6. X6 would be for this constraint where everything will be taken to the right-hand side and equated with x6. So basically, with that in mind, this is how I would, the LP problem would look in a Slack form. So I have my maximization problem. I've just rewritten it or formatted it so that these x's and xi's fall under each other in the column form. Okay, and then I define those x4, x5, x6. And now I have this new representation of my LP problem in the Slack form. Is it clear? Any questions, anyone? Oops, this is too thick. Okay, so now basically when you do it in a Slack form, and the reason why I told you is because if you want to directly do from the standard form to, I'm sorry, LP to Slack form without standard form, then some of you may miss out these additional variables that are actually needed, and you should include them, because then your solution in using the simplex method would not be right. Okay, so that's why if you do it in 2 steps, you are guaranteed that you would do it correctly. Okay. Okay, now look at these variables. So these new variables that we added, the Slack variables, which are on the left-hand side of the equality sign, are known as the basic variables, okay? Slack variables or basic variables. So we assume that, so we have a set B, which has decision variables with indexes 4, 5, and 6. Okay, I'm talking about these indices. These are the basic variables. And the variables which are actually in our objective function and the actual decision variables are known as the non-basic variables. So we have another set n, which is equal to 1, 2, and 3. Clear? So we have a set of basic and non-basic. So what happens in simplex method is sometimes is that actually what we do is we interchange the places of the basic and non-basic, and in doing that, we try to maximize the objective function, and I'll show you how. Okay, so now we know the definition of basic. Basic means Slack variables, non-basic, initially basic means Slack variables, and non-basic means the actual decision variables. But as we apply simplex method, they may change. Okay, so now what I've done is basically nothing much. I've instead of these terms, so what I've done, I've just removed this. I've removed this. I've said that, okay, let's assume that there's this function z, which is equal to the objective function and this. So we want to basically maximize this, which is obvious. It cannot be minimized because we have written it in the standard and Slack form. So this is always a maximize, okay? So we just include that. And this becomes as shown over here. Okay, so this is the Slack form. So when I say write it in the Slack form, this is how you have to write it. Remove the maximize subject to, put a z equal to, and make it beautiful as this. I told you about n and m, so you do not have to worry. And if you want to write it in the general form, so a Slack form would be the tuple n, set b, a, b, c, v, where actually v would be, so we have the objective function z is equal to v plus the objective function that we had. So the v is actually the maximum value that you get for z, and I'll show you how to obtain it, okay? And you have your constraints, which are written in xi is equal to bi minus this, which is a Slack form, and this is a Slack variable, okay? And that's it. So for this previous example that we had, where is mine? So in the previous example, I could have written this also in the matrix form, okay, based on this. So this is the matrix form for that guy, okay? Just take a look at it. I won't waste time. Now, what is this v is equal to 28? I'll show you. I mean, when we apply simplex method, this v will appear automatically. Okay, so for you guys, I've given you an exercise to do. I've given you a problem, and I've asked you to write it in the replaces this thing in what is a matrix Slack form. Okay, so you have to first convert it into a Slack form and then write it in terms of n, b. That's a capital N or even small n. N is the number of indices of the basic set, and m is the number of indices in the non-basic set. A is the matrix of these coefficients that you have for the constraint. We have 3 constraints, so it will be a 3 by 3 matrix. B is this B values on the left hand or right hand side of the equality sign, and C basically is the coefficients of the objective function. Okay, so I've given you the solution also, so good for you. So basically you can just write it and check your answers over here. Similarly, I asked you to convert this into standard form, and this is the standard form. So keep in mind, standard form is less than equal to. Now I've asked you to check whether this function, can you tell me, okay, I want to see if you guys are paying attention or not. Is this a linear problem? Does it have a feasible solution or not? I'm saying show it isn't feasible, so obviously it doesn't have a feasible solution, but how would you show it?
Second equation, probably.
Integration?
Second inequality.
Can you explain? Just explain. So suppose you're teaching me how to show that this is infeasible. Do it for me.
If we change signs from minus to plus, the inequality sign also changes.
Okay.
And in graph, it's like this 2x1 plus 2x2 is greater than or equal to 10. And by just logically thinking, this
Oh,
we
logically.
will not
Well,
have.
you are logical, but for me, if you write it, you think logically. Well, no. You give me a mathematical approach. So mathematically, if you want to show me, this is how you do. I mean, what do you do? Multiply the first one by 2 and then add them, and you would see that when you add them, this would become 0, this will become -3, and 0 is less than equal to -3, which is not correct. This is mathematical proof that this is infeasible. No, infeasible. It's infeasible. It has no solution. Okay. It's easy to understand this, as you said, visualize it logically, but in the exam, please don't write if you think about it logically. This is a logical proof. Just do this and just do this because I need proof. Okay, good. Okay, where are we now? Okay, now we are given a problem. Now we are going to start simplex method. We are given a problem of this form. Okay, so you see that this is already written for you in the what form? What form is this?
Standard form.
Standard form, exactly. So you have a maximize, everything less than equal to, everything non-negative, and you're happy. So this is the standard form. So in order to use simplex algorithm, you have to convert every linear problem into slack form. Keep that in mind, okay? So we have to make this equality. And the reason, the meaning of slack, I'll tell you in the end, but the definition is given over here. It tells you the amount of, so it tells you actually the gap, the amount of you can play with between, or you can increase your objective function to by playing with the basic and non-basic values. So it's the maximum gap between the basic and non-basic values that would maximize your optimization or objective function. So we will look at that once we see the results, and then it would make more sense. Okay. So always convert it into slack form before you start simplex method. So if you convert this guy into slack form, okay, this I've done it for you. You would have your objective function as shown over here, and you would have these three constraints. Okay, I have removed the last constraint because we do not need that in our what we say simplex method, but we should make sure that that is defined, because to make sure that the decision variables are non-negative, as you saw, we have to actually include two new variables, and those two new variables somehow would take part in this, would appear in the slack form. So make sure that is checked. But when you want to start simplex method, you can just remove that default last constraint, okay? So now over here, so we have how many variables? 1, 2, 3, 4, 5, 6. How many equations, constraint equations, which we want to solve? 3, okay? So there are 3 equations and 6 variables. So how many solutions? Many solutions. Good job. So basically, out of this, 6 minus 3 of them should be set to 0 in order to give us a unique solution. Am I right?
Yes.
Good. So if I choose 3 variables out of these 6 variables and I equate them to 0, I would be able to find a solution to this problem. Am I right?
Yes.
Okay, good. So now that's my starting point. The reason why I'm asking you is this is exactly what we're going to do. We're going to find or start with the basic solution. And how do you find the basic solution? By setting all the non-basic variables, that means the actual decision variables that were there in the objective function, to 0. So everything on the right-hand side over here. So we'll be only looking at these 3 constraints, okay? Do not look at the objective function for now. In these 3 constraints, on the right-hand side, set all of these non-basic variables, that means x1, x2, x3 in these three equations to 0. That would give me what? That would give me a solution for x4, x5, and x6. So x4 will become 30, x5, 24, x6, 36. So if I write x1, x2, x3 up till x6, my basic solution would be this guy. Okay, and what does the basic solution mean? It means that if I plug in this value into my z objective function, it would be 0. So the minimum value that I'm starting with for the objective function is 0. And now what I want to do is play or interchange the places of x1 and x2. I'm sorry, interchange the places of the basic and non-basic variables in order to increase the value of c, because it's a maximized problem. Okay, let's see how to do that. Well, I told you. Okay. Okay, so, okay, this is also what I told you. So now let's go back here. So the trick over here is this. I'm going to tell you the trick directly. You look at your objective function, okay? Look at those terms which have a positive coefficient. So in this case, luckily, all three of them have positive coefficients. Okay, so this is +1 and this is +2, right? If there is a negative coefficient, you ignore it in your simplex problem. Okay, you do not actually consider to play around with it. But over here, all the coefficients of all three, x1, x2, and x3 are positive. So all three are candidates. Candidates for what? Now, among these three, you have to choose a coefficient which has the largest value. So 3 has the largest value among 1 and 2. So I take x1. So now I'll be looking at, I'll be starting with x1. The reason why is because x1 increases at a faster rate. That means whatever value of x1 I increase, it would increase the value of z more faster than the other two terms. Am I right? Because of this coefficient value. Correct?
Yes.
Everyone agree with me?
Agree.
Good. So we start with x1. Okay, so we know that if I increase x1, okay, let's go back. Oops. If I increase x1, my value of z will increase. But let's look over here. If I increase x1, the value of x4, x5, and x6 will decrease. So I should be very careful. So I want to find the maximum x1 value that I can plug in such that these three constraints remain positive. That means they do not. So x4 should, x5, and x6 should not become negative. So what is that value of x1, or which of these three equations should I choose? Okay, such that if I make changes to it, okay, so let's look at it. So let's go over here. So if I put x1 over here is equal to 30. Okay, the coefficient of x1 is 30. So if I put x1 is equal to 30, this guy will become 0. But if I put 30 over here, 30 times 2 will be 60. So 24 minus 60 will be negative. So this guy will be negative. So we cannot use 30, right? Let's go here. Now, so 30 is not an option. So let's look at the second equation. In this equation, we have 2 times x1. So 2 times x1, under what condition will 2 times x1 be equal to 24? When x1 is equal to 12, right? Okay, so if I put x1 is equal to 12 in the first equation, 30 minus 12 is 18. So it is positive, so it's good. If I put 12 here, 12 times 2, 24. 24 minus 24, 0, so it's non-negative, good. If I put 12 over here, 12 times 4, 48. 36 minus 48 will be negative, so it will not hold because x6 will become a negative value. So I cannot take 12. So we move on to the next one. Now let's see what this guy has to say. Now, what, so 4 times what will be, so now let's write it. 4 times x1 is equal to 36. So x1 will be equal to 9, right? If I put 9 here, 30 minus 9, positive, check. 2 times 9, 18. 24 minus 18, positive, check. 4 times 9, 36. 36 minus 36, 0, check. So my value of x1 would be 9. So the equation or the constraint that I choose would be the third equation, because the value of x1 that I put here actually is the maximum x1 that I can add or I can include, such that these three conditions, the basic variables do not become non-negative, do not become negative, I'm sorry, okay? So we have to find that equation for which these three equations, these three basic variables do not become negative. So I choose the last equation. When I'm saying I choose the last equation, it means that I'm going to change the place of x1 with the variable on the left-hand side, basic variable on the left. So basically, x1 will be becoming my new basic variable, and x6 will be becoming my new non-basic variable. Is it clear? So keep this in mind. And this is what happens. So I've said, if we choose x1, because the coefficient of x1 is higher than all the other coefficients in the objective function, so I chose x1. I tried to see which x1 value or which equation actually maximizes the value of x1. So we saw that when x1 is equal to 9, that would be the best case because it would satisfy all three of these equations. And it does not allow any of the basic variables to become negative. I've written the same thing over here in words. If I take it to be 30, this is what happens, 12, 9, and the tightest limit is when x1 is equal to 9. Therefore, I choose the third constraint, and I switch the roles of x1 with x6. So what I do basically is now, going back over here, I divide this whole thing by 9, right? I'm sorry, I divide this whole thing by 4, not 9. So I want to make this coefficient 1. So I divide this whole thing by, because I want to now, what I want to do is I want to bring x1 outside, and I want to bring this x6 in place. So x1 should not have any coefficient, so it should be 1. Therefore, I divide the whole equation by 4. If you divide the third equation entirely by 4, this is what you get. Okay, this is the equation that you would get. See that I brought the x6 over here and it's divided by 4, and I remove the 4 coefficient by dividing the entire equation by 4. I bring x1 to the left-hand side, x6 to the right-hand side. So this is my new basic variable now, and this is my new non-basic variable. Now in all the other, basically going back, so now I have an equation in x1 in terms of x1. I have to plug in that x1, and I have to change this as here as well, because now we should not see any x1 on the right-hand side, because now x1 has become a basic variable. So if you substitute this equation in place of all the x1s that you see on the right-hand side, the last one we changed, so this, and this equation, x1 will be replaced and written in terms of x2, x3, and x6, okay? And that's when you get this new set of equations. Okay, and this 27 appears from there. That means if you look at this 9 minus something, so if I put this 3 times 9 minus something, 3 9s are 27, so the 27 appears, okay? So that's how you are actually now getting. So what is this 27? It's saying that if I change the places of x1 and x6, I increase my objective function from 0 to value 27. Is it clear? Guys?
Yes.
So you see now basically these values have changed. Now the structure has changed. Now right-hand side is everything is in terms of x2, x3, x6, and the left-hand side, everything in terms of x1, x4, and x5. So now this is your new set of basic variables, and x2, x3, x6 are your new set of non-basic variables. And this is known as the pivot point. This operation is called pivot. So when you are, when you are changing a basic with a non-basic variable, that operation is known as a pivot operation, okay? And the basic variable which is entering, the basic variable which is becoming a non-basic variable is known as the entering variable. And the non-basic variable which is becoming a basic variable becomes a leaving variable. So x1 was a leaving variable and x6 was an entering variable, okay? So basically you can write this in the same, so these two equations, so this was before having the pivot operation, this is after the pivot operation, but basically these two equations are the same. You solve them, it's the same, right? If you solve them, it's the same thing. Okay, now we continue. So now we have this equation now again. So to continue for the next step, we again go back to the objective function. Look at the objective function. You look at the positive terms with the positive coefficients, not this one, the ones which have the decision variables. So this is negative, we ignore it. Now we have this term and this term. So the coefficient here is 1/4, the coefficient here is half. So which one is greater, 1/4 or half? Half. So then so your next leaving a variable would be x3. Okay. So now that you have x3, you go over here. Now you see that how much you can increase x3. You know that by increasing x3 over here, since it's a minus sign, x1 will be decreasing. Same here, because it's minus, x4 will decrease, x5 will decrease. So it will decrease all the new basic variables. Now you again have to find the limit on this x3 value. And to do that, what you have to do basically is simply just look at the highest coefficient over here. So in our case, if you look over here, I think, yes, I've written it. So if you look at constraint 1, so the maximum, it would be like 18, okay? Because 18 divided by 2 is 9, 9 minus 9, 0. So this will become 0, the smallest value that x1 can take. So this would be 18. The next one would be 42 by 5. And the third one would be 3 by 4, okay? So since we know that this guy is the least, I'm sorry, not the highest. You take the one which is the least, which gives you the least coefficient. So this guy will return the least coefficient, right? Because 4 times, where is it? Sorry, 4 times 3 by 2 is equal to 6, and 6 minus 6 would be equal to 0, which makes x5 the minimum feasible value. Okay, so 3 by 2 among all the other x3 values is the minimum value that you can increase x3 with, such that it satisfies these 3 constraints. And therefore, we choose the third constraint again. So again, we choose this guy. That means now x3 will be leaving, will becoming our new basic variable, and x5, which is on the left-hand side, will be entering. So now we have to write all the equations in terms of x2, x5, and x6. Correct? Clear? And this is what you get. So if you write this last equation, if you bring x3 over here, divide the whole thing by 4, you would get this. Okay? And then you substitute or plug in this wherever you see x3 on the right-hand side. That means in place of this guy, and this guy, you would get a new set of equations, which is given over here. So now you see, you have these guys as your basics and 2, 5, 6 as your non-basics. And now if I substitute, x1 is 33 over 4. x2 is not a basic variable, so it's 0. x3 is 3 by 2. x4 is 69 by 4, x5 and x6 are not on the left-hand side, so they are 0. And if I plug in these values into my z, so z basically only has, we have x2, we have this, x1 is not there, x2 is 0, so this cancels off, x3 is not there, and this is not there, so the only value that remains is this value, and so this is the amount that you have increased z to. Previously, it was, what was it? Z had become 27, and now we increase it to 111 by 4. Okay, so we keep increasing it every time. Now that we have this set of equations, again, we look at the z, the objective function, we find the term containing a decision variable, which is positive. So this is negative, we ignore. This is the only remaining term which has positive, 1 by 16. So we choose this as our next candidate. So this will be our leaving variable. And now we have to see for what value of x2 we have to choose. We have to see which equation we have to choose as our pivot equation, such that the basic variable would become the entering variable. So you do the same thing that we discussed earlier for the previous 2 cases. And we see that the 3 constraints would give us the bounds on 132, 4, and infinity. So obviously 4 is the minimum one. So we take x2 to be our leaving variable. And so which equation gave us the second equation? And x3 will be our entering variable, okay? Because this is the first equation, second equation, third equation. So this second equation gives us the limit for the value of x2. Okay, so we increase x2 to 4, okay, and it becomes our new non-basic variables. So we solve for x2 and we bring it on the right-hand side, as you see over here. I'm sorry, left-hand side, and everything else on the right-hand side, and then you get this. And again, when you put x1 8, x2 4, x3 0, x4 18, x5 and x6 again 0, and you plug these values into the z function, you would get objective value of 28. Now, what happens next is nothing happens next. Why? Because now we go back to the objective function to go for the next iteration, but we see all the terms having the decision variables are negative. So we have nothing else to do. We are done, and the optimal value for this z for this LP problem would be 28. Okay. Is it clear, guys?
Yes.
Yes.
Good. So now let's look at this. So the values now what we get for the slack variables, okay? So the slack variables initially were variables x4, x5, and x6, right? Correct? So
Yes.
this is x1, x2, x3, x4 is 18. So what does it tell me? It tells me that, okay, now then we have to go back to the very original equation, which is this equation. So x4 was included in our slack form in first equation, in first constraint, right? Now what happens if x4 is 18? Just see, 30 minus 18 gives you what?
12.
12. Okay. Now what does this tell you? Go back.
X1 should be 8, x2 4.
Where's that for me? Ah, here. What does that tell you? x4 was included in the first constraint over here, okay? We found the values for x1, x2, x3, okay? And x4 would be equal to 30 minus 18, which is 12. So basically, what does that mean? Come on, someone.
X1 is 8, should be 8, and x2
That means
4.
x1, x2, x3, the sum of them should be equal to 12, right?
Yes.
So it means that I have found the value of x4 such that to the slack value is that means x4 has a gap of 18, okay, between the optimal solution and the best solution for the variables x1, x2, and x3. So for the best x1, x2, x3, okay, that would give us the optimal solution. The difference between the final difference would be 18. Okay, between those variables, because you add them up together and you minus it from 30, which was in the original equation here, and you see that would be the value of x4, which we get over here. Similarly, for x5 and x6, it's 0 because it doesn't sum up to anything. It's sum is 0. We have used all the slack for x4 and x5. There's nothing else that we could have added. Okay. Well, that's it. That's it. And well, yeah, there are some videos because I believe some people like watching videos probably. These are the lectures that I found. One is from a university, Penn State University, where the professor explains about this. You can look at that. Another one is a YouTube video, which you can, it's 5 parts and it explains it on by writing it down. So basically it may help you. I think I have tried my best to explain it as clear as possible. Next time we will go to the lecture 6A and I'll tell you what's the difference between the two. Basically, they are the same. You can, but in exam, I would prefer you guys to follow this approach, which I've spoken in lecture 6B, because it's more easier to follow both for you and for me when you solve it. Okay. So now you have used simplex method to solve. So using simplex method, now you can solve any linear problem. Next time, we will also talk about the KKT condition for equations. So the equation that we have seen over here, they were like very small. And if finding the optimality condition was easy, you could solve it with paper if the number of equations is not, a number of decision variables are not very high. But what happens if you have many more decision variables? Solving it by hand may take too much time. So we have to find some condition, optimality condition in a convex hull for solving linear programming problems. And that's known as KKT condition, which we'll talk about next time. Any questions?
No, I think.
No.
Good. So please study. You do not have a quiz next week, but you will be having an assignment. So study hard, learn KKT. I'm sorry, learn linear programming till what we have studied so far. And I'll meet you on Tuesday. Okay?
Okay.
Thank you.
Okay, thank you, Professor.